In this video, we are going to discuss like a bigger example, an example or a circuit that has two transistors, Q1 and Q2. One of them is NPN and the other one is PNP. And as you see, the first transistor is connected to this voltage divider. The base of the first transistor is connected to a voltage divider with 15 volt, 100 kilo ohm, 50 kilo ohm. And this is one of the methods that we use in order to bias the transistor, as we will see later, in order to make the transistor operate or work at a certain operating point. There are many biasing techniques. One of them is to connect the base to a voltage divider like this. However, if we try to analyze the base emitter loop of this transistor using or under this structure, under this voltage divider, the analysis will not be easy. That's why if you see this structure in a circuit, try always to replace with the Thevenin equivalent circuit. So try to remove this part of the circuit and replace with the Thevenin equivalent. So replace this part with its R Thevenin and V Thevenin. This will make the analysis of the base emitter loop much easier. And then after you solve the circuit, you can go back, after you calculate, for example, V base, you can go back to the original structure and you calculate the currents in both resistors. But it's easier in the beginning. Once you see this structure, this voltage divider connected to the base, try always to replace it with the Thevenin equivalent resistance and Thevenin equivalent voltage, and this will make it easy to you. So in order to do that, this is our voltage divider, and we want to replace it with the Thevenin equivalent voltage, R Thevenin and V Thevenin. This is 100 kilo ohm, this is 50 kilo ohm, and this is 15 volt. We know that R Thevenin, first we know that V Thevenin is the open circuit voltage, the open circuit voltage. So you assume that the terminals here are open circuit, and you calculate the voltage across the 50 kilo ohm. So V Thevenin will be 15 multiplied by 50 over the summation, over 100 plus 50. So this will give you 5 volts. So V Thevenin is the open circuit voltage. You assume that this terminal is open circuit, and you calculate the voltage between this terminal and the ground. And of course, if this terminal is open circuit, then the voltage between this terminal and the ground can be calculated from a voltage divider, 15 multiplied by this resistance over the sum, which is 5 volt. And then in order to calculate R Thevenin, what you need to do is you remove or deactivate the voltage source. If you deactivate the voltage source, so you connect the 15 to ground, so you will get a structure that looks like this. This is 50 kilo ohm, 100 kilo ohm. And looking from here, what is the resistance that you will see? You will see 50 parallel with 100. So you can draw this in a different way. You can draw this like this, 50. And then you have 100 between this point and the ground. So R Thevenin will be 50 kilo ohm parallel with 100 kilo ohm, which will give you around 33.3 kilo ohm. So like this, we calculated using the same basic rules that you learned in the circuits course. You calculated V Thevenin and R Thevenin, and now you can replace this part of the circuit. You can replace this part of the circuit with the equivalent Thevenin circuit. So you can replace this with R Thevenin, which we calculated to be 33.3 kilo ohm, and a voltage source, V Thevenin, which is 5 volt. This will make the analysis of this loop much easier than before. So now let's remove this calculation for the Thevenin equivalent, and now we try to solve our circuit. In order to solve our circuit, we'll go on the same procedure. Assume, solve, check. But now we have two transistors, so we have to assume the status of each transistor. And as usual, we'll start by assuming that both of them are active. So assume both Q1 and Q2 are active. In this case, this is I base 1 since we have two transistors, we have to call everything 1 or 2. I base 1, this will be I base 2, this is P and P, so I base 2 will be going outside. So this is I base 2, this is IE1, and the current here is I collector 2, the current here will be IE2. What about the current here? Don't do the mistake. Don't say that this current is IC1, because this is not IC1. IC1 is the current in the collector of transistor number 1, which is what? Here, the current here, not the current here. The current here is IC1. So IC1, the current of the collector of the first transistor, is the current here. It's not here. This is a common mistake, so you have to be careful. Don't say that this current is IC1, because IC1 is the current going in the collector. The current here is not IC1, it's a mix between IC1 and IB2. So you can apply Kirchhoff current law, and you will see that the current here, the current going in this resistor, is IC1 minus I base 2. So now we named all the currents in our circuit. If we assume that both transistors are active, then also we know that this voltage will be 0.7 VEB of the second transistor, and this voltage VBE of the first transistor is also 0.7. Now what we can do, we can start with the base emitter loop of transistor number 1 of Q1, and we say that 5 volt equals the drop here plus 0.7 plus the drop here. So 5 volt equals 0.7 plus the drop across the base resistance IB1 RB1 plus the drop across the emitter resistance, which is IE1 RE1. And we know, since this transistor is active, there is a relation between I base 1 and IE1. IE1 is 1 plus beta I base 1, and now we know the resistors RE1 and R base 1, and we have one equation in one unknown, which is I base 1. So we can, from this equation, we can calculate I base 1 to be 0.0127 milliampere. Once we calculated I base 1 and we assume that the transistor is active, we said before that in the active mode, if you know one of the currents, you will be able to calculate all the currents. So you can say that IE1 equals 1 plus beta I base 1, and beta is 100, of course. So this will be, IE1 will be 1.29 milliampere, and you can say that IC1 is, again, beta I base 1, which will be approximately 1.27 or 28 milliampere. So now we calculated all the currents of transistor number 1. Let's take transistor number 2 now. Before we take the collector emitter current of transistor number 1, okay, to calculate or to check for VCE1. Before we check for VCE1, we need to calculate I base 2, because in order to take this loop, still we don't know what is I base 2. So in order to know what is I base 2, we have to go and solve the emitter base current of transistor number 2. So what we'll do, we are going to solve emitter base loop of transistor number 2. The emitter base loop of transistor number 2 says what? Says that 15 volt minus the drop here plus 0.7 plus the drop here equals 15. So basically 15 will cancel with 15. If you take this loop, it's like these two sources, they are short circuit, right? They have the same volt exactly. So if we take this loop, you have a drop here, 0.7, you have a drop here IE2 RE2, and you have a drop here, which is this current multiplied by RC1, right? So KVL, applying KVL in this loop, says that IC1 minus I base 2 multiplied by 5 kilo ohm equals the two other voltages, which is 0.7 plus the drop here, which is IE2 RE2. And IE2, of course, RE2 is 2. RE2 is 2 kilo ohm. And IE2 has a relation with IB2, right? IE2 has a relation with IB2. So let's do it in the next step. So IC1 we already calculated to be 1.27 milliampere minus I base 2 multiplied by 5 kilo ohm equals 0.7 plus IE2. IE2 we can write it in terms of I base 2. 1 plus beta I base 2. 1 plus beta I base 2 multiplied by 2 kilo ohm. So now this is another equation, an equation in I base 2. Everything is known, beta is 100, and the only unknown here is I base 2, so you can calculate I base 2 from this equation, and it will turn out to be I base 2 0.0275 milliampere. Once you calculated I base 2, you will be able to calculate all currents of the second transistor, IE2 and IC2. You will find that IC2 will be 100 multiplied by I base 2, so it will be 2.75 milliampere, and IE2 will be 1 plus beta multiplied by I base 2, so IE2 will be 2.78 milliampere. So this is equal beta I base, and this is 1 plus beta I base. Okay, so now we have all the currents of both transistors. We have the currents of transistor number 1, the currents of transistor number 2. Now we can calculate VCE1 and we can calculate what? VEC2. And we can check whether these two transistors are active or not. So let's start with VCE1. So we'll consider here the collector emitter loop of transistor Q1. The collector emitter loop says that 0 plus the drop here plus VCE1 plus the drop here equals 15, right? So 15 equals 0 at the ground plus the drop here IE1 RE1 plus the drop here VCE1. This is the unknown. Plus the drop at this resistance RC1 multiplied by the current IC1 minus I base 2. So plus IC1 minus I base 2 multiplied by RC1 equals 15. Okay? So IE1 already, we calculated IE1 to be 1.29 milliampere multiplied by RE1 3 kilo ohm. And don't forget, you can use the volt with milliampere and kilo ohm. So if you use kilo ohm, you can use milliampere, it will give you volt. If you use ohm, you have to use ampere to give you volt. So here we are going to use milliampere and kilo ohm. Okay? Plus VCE1, this is the parameter that we want to calculate. IC1 minus I base 2, 1.27 milli, minus I base 2, which is 0.0275 milli, multiplied by RC1, which is 5 kilo ohm. Now the only unknown in this equation is VCE1. If you calculate VCE1, you will find that it is equal to 4.87, which is greater than VCE saturation, which is 0.2. Then our assumption for transistor number 1 so far is correct. So it's correct for transistor number 1. So Q1 assumption is correct. Let's look at Q2. We need to check for VEC2. So we'll take or we'll consider the collector or the emitter collector loop of Q2. So consider emitter collector loop of transistor Q2. From this loop, we'll be able to calculate VEC2 by saying that 0 plus the drop here plus the drop here, which is VEC2, plus the drop here equals 15. So 0 plus IC2, RC2 plus VEC2, this is the parameter that we want to calculate, plus IE2 RE2 equals 15. Of course, we know IC2. IC2 is 2.75 milli multiplied by RC2, which is 2.7 kilo ohm, plus VEC2, this is the parameter that we want to calculate, plus IE2, which is 2.78 milli multiplied by RE2, which is 2 kilo ohm, equals 15. From here, you'll find that VEC2 is the only parameter that is unknown in this equation. You can calculate VEC2 equal to 2.015 volt, which is again greater than VEC saturation, which is 0.2. Then our assumption for Q2 is also correct. And once we found that Q1 assumption is correct, Q2 assumption is correct, then our whole solution now is correct. We can also go back and calculate. We can go back and calculate the original circuit, the currents and voltages of the original circuits, that we replaced with Thevenin equivalent. So we had an original circuit like this in the beginning, 100 kilo ohm and 50 kilo ohm. This is, we calculated the base current here, I base 1, and this is V base 1. We can say that V base 1 equals the drop here plus 0.7. So we can say that V base 1, I'm going to remove, or we can write it here. We can say that V base 1 equals 0.7 plus the drop across this resistance, IE1 RE1. IE1 already calculated to be 1.29 milli, and RE1 is 3 kilo. So you can calculate VB1. Once you calculate VB1, which is the voltage here, you can calculate the current here. Let's call it I1, and you can calculate the current here. Let's call it I2. You can say that I1 equals VB1 minus 0 over 50 kilo. And you can say that I2 equals 15 volt minus VB1 over 100 kilo. 15 minus VB1 over 100 kilo ohm. So you can calculate everything about your circuit, and it is confirmed that both transistors are in the active region. That was like a big example. Of course, if it turned out that one of the transistors is wrong, then you will have to change your assumption for the whole circuit. And I advise you change your assumption only for the transistor that turned out to be wrong. Keep the one that was correct as it is and change only the transistor that was wrong. For example, if Q2 turned out to be not active, then you assume that Q1 is active and Q2 saturation, and you repeat your whole solution once again. Of course, the solution will be more difficult if one of them is saturation, and I want you to think about how you are going to solve that. If one of them is saturation, for example, assume that it turned out that Q2, as our assumption for Q2 is wrong, so you have to assume that Q2 is saturation and Q1 is active. Repeat the solution again. Imagine that. Repeat the solution again, and just without numbers, and just try to see how you are going to solve this problem in this case. If you assume that this is active and this is saturation, or the opposite case, this is saturation, this is active, try to see how you are going to solve this circuit. There will be one more example in the slides. I will leave it to you to try to solve by yourself, and maybe I will give it to you as a class assignment later. Okay? We'll see you in the next video.